Okay, I have this particular topic today. Hi, Bashir. So this particular topic today. So as I say, there are only very few people so far. So I'll go slowly, try to explain the concepts. If you don't understand something, stop and ask me questions. All right? It's a bit more abstract than before. Okay. So we want to get into synchron algorithm, but before that, I want to talk a little bit about back to autocalculus. So let's start by having something back to autocalculus. And what did we learn about autocalculus? We turned the set, which is P2 of RD, equipped with the Wasserstein 2 metric, to a formal Riemannian manifold. And how do we do this? Is that if you take some rho in this Wasserstein space, P2 of RD, you define some kind of tangent space. You define the tangent space of rho. This is some subspace of L2 velocities. So this is a subspace of L2 of rho. And if you have one such velocity, some v in this tangent space, you can measure its size by looking into its L2 norm. It's by its L2 norm at rho. So this is like a local picture of the size, and the global picture of the distance can now be recovered from this local picture by Benamo-Brinier. So you can write down what is the W2 distance between some mu and nu as the infimum over the length, the integral of the length of every Vt dt from 0 to 1 over all smooth curves with their tangent velocities. Okay. So rho tvt over some smooth curves. Now, one of the interesting developments in the last few years is a generalization of this setup of auto, where you look into different kinds of metric tensors and you derive different kinds of processes out of it. So one of the benefits that we get from this is that in this setup, I can talk about the heat flow is the gradient flow of entropy. So this is one of the consequences that we derive. And now the idea of the gradient flow of entropy is metric dependent. And so one of the interesting things that is happening in the last few years is this to experiment with different kinds of metric and associating different processes with it, which are often very useful. So here is a following generalization. Here's a generalization of this idea. Let's take some convex function, some smooth convex function from RD to the real line. And now instead of looking into take some rho. So take some rho in P2 of RD. And now if I look into a function V in its, I will write down exactly in some appropriate space. This is going to be some kind of tangent space. I can define a new size of V by U by defining that this is V transpose of X, Hessian of U of X, V trans V of X dx. Sorry. d rho x. So what have I done here? What I have done here is that I've changed the notion of the size of a tangent, the norm of the size of a tangent, from its usual L2 norm to something that depends on this Hessian of the convex function. Now, if you do this, then you get a new notion of distance of the tangent space. You actually get a new tangent space itself out of it. You can talk about the new tangent space, this new tangent space of rho itself, as the closure of the gradient of G, as the closure of gradient of G, so I want to use the word G, gradient of psi, where psi is some Cc infinity of Rd. And now you take this closure under this new norm. Do you see what's happening here? So I'm changing my L2 space by having this new kind of inner product using this Hessian of a convex function. And I'm looking into a new kind of tangent space. Now I can also define a new metric out of this by simply looking into the same idea over here. I'll get a new Benamo-Bernier formula out of this. There is something to say about the metric, but that's not particularly important here. What is the important thing here is that by defining a new metric tensor locally on the tangent space allows me to generalize this Riemannian framework and allows me to talk about, okay, now what is the gradient flow of Hilbert's of different quantities like entropy or Kullback-Leibler in this. So one can ask, what is the So what are the gradient flow of KL in this structure? Do you understand what I'm trying to do? I'll come to this, see why we are doing this, but is this clear what we are trying to do here? So you're generalizing the Otto's idea of the Riemannian tensor is, and creating a new geometry, and we're asking, can I associate other processes in some sense, like talking about what is this gradient flow of Kullback-Leibler. So it's not going to be Langevin, it's not going to be the heat flow. What are they going to be? Okay. Now, this particular case that I've written here, which is given by this Hessian of a function, of a convex function u, is particularly special. There are many reasons why this is special. I will try to motivate this from an optimization point of view, because that's how originally I got into it, but there are other reasons why this is a very special construction. So let's talk about some kind of Euclidean counterpart of this. Now, in the Euclidean space, you can do the same thing. You can have on the Euclidean space, you can look into the norm of x to be just the Euclidean inner product x dot x. Or you can say, okay, I have a function u, which is from Rd to R, which is convex. Let's say strictly convex. And I have its Hessian of u of x. And I can say like, okay, I can now measure the norm of this new norm here of u as x transpose Hessian of u of x dot x. Okay, I can do this. This is what you get out of this is that you have distorted the flat Euclidean geometry to a geometry of something that is called a Hessian geometry. The flat Euclidean geometry is now distorted by introducing a curvature. Is now distorted. And the resulting manifold is called the Hessian manifold. It's called the Hessian manifold.
Seems
To
like
see,
you
sorry,
recover.
go ahead.
It
Go ahead.
seems like you recover the like regular norm just if U is quadratic.
That is exactly correct. In particular, if I take u of x to be 1/2 of norm x squared, then of course I have recovered. So this is Hessian, by the way. The Hessian of u of x is identity. And I've recovered my usual geometry out of this. So this is a generalization of this Euclidean construction. But the reason I want to do this is for some particular choices of u, as you will see, this becomes very, very useful in optimization. So let's see some examples. Let's see some examples of gradient flows in this new Riemannian geometry. So what are gradient flows in this new Riemannian geometry?
Do we need U to? Okay, U is. I was just thinking about negativity. So U is convex. Does that like
U is,
prevent the
yes,
norm from being negative?
that's right. So U is always is strictly convex, and most of the times you assume that it has a lower bound. It's uniformly convex,
Okay.
or even has sometimes even has upper bound.
Okay.
Yeah. So let's ask the question: what are gradient flows in this Hessian manifold? In this Hessian manifold, in optimization language, these are called mirror coordinates and mirror gradient flows. So in optimization language, these are called mirror gradient flows. And there's a reason for this. The reason is that the point x going to the gradient of u of x, this is seen as some kind of like dual global charts. So these are like dual global charts of this manifold. So you can represent the manifold as just by the chart x, just the Euclidean chart x, or you can represent it by the gradient of u of x. You can also go back from the one to the other by looking into gradient of u star. But this gives some kind of mirror images. So x and gradient of ux is like representing the same point P on the manifold. They're just mirror images of one another. And this is a very useful way to look at this because there's a hidden duality that comes into here, which only gets clear when you think in this term, that there are two coordinate charts and things will look different if I write them in this coordinate charts, but they're essentially the same object. So let me show you why optimization people care about this by writing some examples here. So the main thing that people in optimization care about is that often these mirror gradient flows can converge faster than Euclidean gradient flows. They can also converge slower depending on the problem. So mirror gradient flows are not Euclidean gradient flows. They can display a wide range of behavior. Display a wide range of behavior. As I said, please ask me questions. This is really at the cutting edge of research and involves a lot of ideas. Ask me, stop and ask me questions. Display a wide range of, sorry, go ahead. Mm-hmm.
Is there any connection with mirror gradient descent, or is it just a
These
coincidence
are
with
the
terminology?
continuum versions of mirror gradient descent. That is absolutely correct.
Mm.
So if you're in optimization, you've probably heard of mirror gradient descents, which are like implicit Euler with the Bregman manifold. So if you take the continuum limit of this, you get this mirror gradient flows. That's correct. So here is some example. So I'm going to talk about some particular function, and I'm going to look into, say, dimension d equals to 1. So how does this mirror gradient actually look like? So let me just say, for example, how does it look like? So the mirror gradient flow always has this formula. I'll just simplify my matter. I'm going to take dimension d equals to 1. And the mirror gradient flow for a function f from Rd to R. You should really think of this on the manifold. I'm writing Rd, but Rd is really a manifold here. It looks like this. It satisfies the following ODE, which is x dot t is equal to minus u double prime xt inverse f prime of xt. Now, if you're in general dimensions, you would write xt dot is equal to minus Hessian of u of xt inverse gradient of f of xt. Yeah, I'm just going to stick with this dimension d equals to 1. That's the ODE that is satisfied by this mirror gradient flow. Now let's take some particular examples and see how this behavior is drastically different. So I'm going to take d equals to 1. I'm going to take the function fx equals to x squared over 2. Very simple function. Now I know that f prime of x is x, and I also know that the unique minimizer is at the origin. It's a super nice function, is at 0. Okay. Now let's see what kind of mirror gradient flows do I get. So example 1, which is take ux equals to x squared over 2. Now this one is just the Euclidean gradient flow. As I already said, if you take one half norm square, you get back your Euclidean flow. So then I'm looking into xt dot is equal to minus xt. That's my solution. And in case I can exactly solve for xt, and I will get xt is equal to e to the power minus t. So I'm going to always start from x0 equals to 1, always. So xt is e to the power minus t. So this, of course, converges to 0 as t goes to infinity. And this is exponentially fast. Right? That's my Euclidean gradient flow. Here's my example 2. My example 2 is I take ux to be ux is equal to x to the power 4. Now, if you write down ux equals to x to the power 4, I get that u double prime of x, this is 12x squared. And so I'm solving for xt dot is equal to minus 1 over 12x squared. And then f prime of xt, which is just xt. So xt, which is just xt. And so this gives me minus 1 over 12 xt. I can also solve for this guy with x0 equals to 1 again. I can also solve for this guy, and I would get xt is equal to square root of 1 minus t over 6 plus. So what's the biggest difference that you see from this guy from the previous guy? As t goes to infinity, this one still goes to 0, but the convergence is much faster than exponential. It converges in finite amount of time. At t equals to 6, I've already hit the origin. So it converges in finite amount of time. Do you see what I'm saying? Does this make sense? So this is an example whereby bending my space to create a new manifold, I have managed to make my gradient flow converge much faster. A flip side of this is example 3, where I would look into take ux equals to 1 over x. Now, if you do this, then what do I get is u double prime of x. Well, that's minus 2 over x cubed. So, sorry, plus 2 over x cubed minus. And now if I write down what is the mirror gradient flow, I get this is minus 2 over xt cube inverse xt, which is minus, xt, which is minus 1/2 xt to the power 4. Again, x0 is equal to 1. I can also solve this, and I get xt is equal to 1 plus 3t over 2, negative 1/3. As t goes to infinity, this again converges to 0. But now the convergence is much slower. In fact, this is converging like t to the power minus 1/3, so it's polynomial.
So are we minimizing u?
No, I'm minimizing f. F is x squared over 2. At every example, I'm minimizing fx is x squared over 2.
Got it. Yeah, got it.
U is generating the geometry.
It's how we're distorting the space. Got it.
Oh, I'm distorting the space. Do you see what is happening? Do you see the relationship between f and u? So it clearly displays a wide range of behavior compared to my Euclidean gradient flow. But do you see why sometimes it's faster, sometimes it's slower? What is the thing that, I don't know, strikes you here? What is leading to this behavior? Like look at the equation here. Look at the equation of the gradient flow. What do you see? Any intuitive guesses why we are seeing this kind of behavior? Sometimes it's much faster, sometimes it's much slower.
I wonder if it depends on the value of the Hessian of u, just like if it inverse, right?
Correct.
So if the
Correct.
Hessian is smaller when it approach the minimum
Minimum,
value,
exactly.
then you get inverse and you converge.
That is absolutely correct. That's a very good observation. That is absolutely correct. So the behavior is determined by the Hessian of u near the minimizer of f. And if the Hessian of u is very small, close to the minimizer of f, you get a very fast convergence. And if it is big near the minimizer of x, then you get a slow convergence. Right? That's exactly correct. Good. Let's try to do this on the Warschachtschen space. So if you're back to the Warschachtschen space, take this convex function u. This is again strictly convex. Okay. And I define my, say if I take my rho in P2 of Rd, I define my new metric tensor to be V transpose of x, Hessian of u of x, V of x, rho x dx, Ohm squared. Good. And I can ask the question that if I take some measure, let's say mu, which is e to the power minus f, what is the gradient flow of Kullback-Leibler with respect to this new tensor? What is the gradient flow of KL with respect to mu in this new setup? The relationship between this question and this Hessian manifold is not obvious. The relationship is that whatever we have been doing so far for the Euclidean spaces and constructing my Wasserstein space on Euclidean spaces can also be done for manifolds. And this new space, Wasserstein space, is nothing but the Wasserstein space over the Hessian manifold. So what do I mean by this? This is a non-obvious connection. So then aside is that if my Mg, if this is my Hessian manifold, given by U, I have a certain distance square on this Hessian manifold. Sorry, the distance square function on this Hessian manifold, right? So this is my square distance on this manifold. And if I have two probability measures, mu and nu, I can define my W2 square G on mu and nu by minimizing the integral of d square xy gamma over couplings. That gives me a certain Wasserstein square distance over probability measures on the Hessian manifold. Everything else remains the same. And now with respect to this Wasserstein square, I can ask the question, okay, what is autocalculus? What is the gradient flow? And that basically boils down to this. By the underlying space, you change the norm of the tangent space by looking into this V transpose Hessian of U, V of x rho x dx, and you ask what is the gradient flow of Kullback-Leibler. Okay, this is my new Wasserstein space. Does this make some sense? As I said, it's not obvious. There's something to be proved here, but this proof has been done in a paper of Lizini. But I hope it makes some kind of intuitive sense that whatever we have been doing so far for Euclidean spaces, and can also be done for manifolds. And if you take the manifold to be this Hessian manifold, then what you get back is this generalization of the autocalculus. Okay.
Sorry, what is G?
Oh, G is the metric tensor. This is the metric tensor. So
okay,
that's this
defining
guy.
the manifold.
Yeah, that's this guy. Where did I write it? Over here.
The U.
Yeah, exactly. The new norm,
Got it.
basically. Yeah.
Okay.
That's right. So I don't want to write RD because you really should not think of it as a flat space. It's some manifold with two dual global charts. But on this manifold, you create the Wasserstein space and you see this happening. All right.
So the square distance is based on the G, right? Your D square is based on the G, right?
That's right. So D square would be given by, exactly. So D square would be given by the infimum. This is the infimum over all curves. So if you say D square between 2 points, P and Q, you would be looking into infimum of all curves, xt, such that x0 is P, x1 is Q, and this is like the integral of the x dot t with respect to this new norm G dt. Exactly.
Okay, thank you.
Good. Any other questions? Okay. So what can we say? So this actually has been known. This process, which has appeared a few years ago, has become very important now, that this corresponds to, that this gradient flow of Kullback-Leibler is what corresponds to what people call now the mirror Langevin equation. This is the mirror Langevin diffusion, I would say here. So diffusion of the mirror Langevin Fokker-Planck equation. So what do I mean by this? That there is a certain SD that satisfies this. So there's a certain SD that you can satisfy. So dxt, I'm going to write some dt plus something over here, which is dbt. I'm going to write these terms there. So it satisfies a certain SD such that the marginal distribution of this xt, such that the marginal distribution of this SG gives me the gradient flow of Kullback-Leibler. Okay. So before I give you what these SD is, so let's ask this question. What happens when U of X is 1/2 norm square? What is the process that I get? What is the process that I get? So when Ux is equal to 1/2 norm square, then all these fancy manifold things simply boils down to my Euclidean geometry. There is no particular change in the curvature that's happening here. It's completely Euclidean geometry. And so in that case, if I look into a process which is mu, which is e to the power minus f, and I ask what is the gradient flow of Kullback-Leibler with respect to e to the power minus f, what is the diffusion that I get whose marginals gives me this?
I think the overdamped Langevin equation, right?
That's right. This is the overdamped Langevin diffusion. So in general, I get that this is the overdamped Langevin diffusion. I'll write down this here. So when Ux is equal to 1/2 norm x square, and I have mu is e to the power minus f, I get dxt is equal to minus gradient of f of xt dt plus square root of 2 dbt. Okay, that's what I get from here. Now here, on the other hand, what will I get is that I will get something slightly different. So over here, so dxt, so I want to reach e to the power minus f. Call nu to be the push forward of mu by the map, which is the gradient of the convex function. Okay, so mu is here. I can think of my gradient of my convex function as a Brenier map that is transporting mu to nu. All this to be the subject nu. And suppose this is e to the power minus v. Okay. In that case, what I will get for this new mirror Langevin diffusion is that I would get dxt is equal to minus gradient of v applied to the gradient of u of xt dt plus square root of 2 the Hessian of u of xt dbt. Okay, it looks somewhat complicated, but trust me that there's a very natural way to see this object. It just looks complicated. I'm going to say this is inverse. Okay. Now check that you get back your Langevin diffusion when your u is 1/2 norm x square. When your u is 1/2 norm x square, your gradient of u is identity. Your gradient of u is identity, then nu becomes equals to mu, and the Hessian of u is just identity. Sorry, the gradient of u is the identity map, and the Hessian of u is the identity matrix. And so what you get back is that this term will coincide with that term. This term will coincide with that term. And your middle Langevin diffusion converges exactly to your usual Langevin diffusion. Do you understand this? It looks more complicated, but it really, you should think of it as something very structurally very similar. It is nothing but the gradient flow of Kullback-Leibler with respect to a fixed measure, which is e to the power minus f. How do you feel about this? Do you feel?
Yeah,
do
I'm
you
just
understand?
trying to look at the grad V term.
Yeah.
And match it up with grad F.
Right. So when u is identity, so sorry, when ufx is 1/2 of norm x square, then nu is equal to mu. So v is equal to f, and gradient of u of x is equal to x. The Hessian of u is identity. Now just check that you get back the same expression.
Oh, V is equal to F. I see.
Right. What do you think? Make sense?
How should I think of V here? Like
So,
not in this case where we recapitulate V equals F, but in general?
You should think in terms of, again, in terms of mirror coordinates. Is in this over here, I tried to give this idea that x and gradient of u of x, they should think of it as dual. They're like counterparts of each other. And over here, there are two probability measures. One is mu, and the other is nu. And they're like mirrors of one another. You're basically seeing the same measure through two different coordinate systems.
Okay.
And so they look different, but they're really like they're basically mirror images of one another. That's what that's what the change of coordinates of the
So in
manifold
like the mirror
does.
dimension, we have V instead of F.
Correct. And so you should interpret. So there's a very, very nice way of interpreting these gradient flows here. So the way that you interpret this is that xt dot is the negative of the gradient with respect to the mirror coordinate of the function f. So if I call xt, so if I call, let's say, yt to be the gradient of u of xt, this is my mirror coordinate, then this thing becomes xt dot becomes minus a gradient with respect to yt of f. And over here, what I'm doing is something very similar. I'm looking into this gradient of v with respect to the mirror coordinate here. So there's a very close parallel of these objects with respect to mirror with respect to mirror descent. They're just doing things in the probability space.
Oh, that's a grad of V evaluated at.
That's right. That's a grad of V evaluated at the mirror gradient of u of xt.
Okay.
How are you? How are the rest of you feeling? So this is a stochastic process which has become rather important these days, mostly from the applications to machine learning. If you search by middle Langevin diffusions, you'll see several hits. Again, this is because in many applications, this seems to converge faster than your usual Langevin diffusions. We don't quite fully understand when or why and how much and so on, but that's the reason why people like it. But the similarity with the Langevin diffusion is that they are both gradient flows of Kullback-Leibler with respect to the transition, with respect to this terminal density. By the way, xt converges to e to the power minus f as t goes to infinity. But the underlying geometry is different. Underlying geometry in one is Euclidean. The underlying geometry of this one is this mirror geometry, the Hessian geometry that you get from the Hessian of U. Cool. Now, to get to sinkhorn, let's ask the following question. So let's go back to sinkhorn. So this is taken from a paper that I wrote with Younghan. So this is a paper. This idea is taken from a paper of Dave, Kim, myself, and with Jeff Schebinger. Where we analyze what happens to the sinkhorn algorithm as the temperature parameter goes to 0. And we show that how this is related to this mirror geometry that I have described so far. So let's go back to the sinkhorn algorithm. So suppose I have two property measures, mu, which is e to the power minus f, and nu, which is, let's say, e to the power minus v. So these are two property measures. And now I run my IPFP algorithm, so run my sinkhorn algorithm in continuum. So sinkhorn for some epsilon positive. So when I run my sinkhorn algorithm for this epsilon positive, so what am I getting? So recall, if I write things in a matrix form, there would be, of course, this is happening in continuum. So if I write this in a matrix form, at every alternate steps, I would get nu is so these are my row sums. So these are my column sums, which are nu, which is e to the power minus v. And these are my row sums, which is mu, which is e to the power minus f. Now, at every alternate step, one of these is going to be achieved, and the other one is not. So at each alternate step, iterate, my x marginal is going to be e to the power minus f, and the others x is not going to be my e to the power minus f. X marginal is e to the power minus f. Right? I've explained this. How does this happen? At every step, you if the marginal is not e to the power minus f, you look at the marginal, divide by the marginal, multiply by e to the power minus f to get the x marginal e to the power minus f. Now the y marginal is not e to the power minus v. So in the next step, what you do is that you compute the y marginal, divide by the y marginal, multiply by e to the power minus v to get the y marginal e to the power minus v. Now this has destroyed the x marginal. Now you fix the x marginal, destroy the y marginal, fix the y marginal, and go back and forth. Now let rho k epsilon, for k equals to 1, 2, 3, etc., denote the sequence of x marginals that are not e to the power minus f. So these are the times when the y marginal is e to the power minus v, but the x marginal is not e to the power minus f. Now, I'm assuming that the sinkhorn converges here, which we are sure that the sinkhorn will converge. I know that this limit, as k goes to infinity of rho k epsilon, this is going to be e to the power minus f. Okay, but none of these rho k epsilon themselves are going to be e to the power minus f. Now, what we want to understand is what happens to the sequence as epsilon goes down to 0. So this is a sequence. So what I'm going to do is that I want to understand what happens to the sequence as epsilon goes down to 0. So what am I going to do here? What do I mean by this? So first, I'm going to embed things in continuous time. So let rho t epsilon be rho k epsilon when t is between k epsilon and k plus 1 epsilon. So I have this sequence of measures, and I'm just going to draw lines to make this in continuous time. And the length of each of these lines is epsilon. Does this make sense? So I've embedded my sequence in a curve that admits jumps, and then I look at this curve in time t, in continuous time t. And so this is for t greater than or equal to 0. Now, once I have this curve, I can ask the following question. As epsilon goes down to 0, is there an absolutely continuous curve rho t, t greater than or equal to 0, such that okay, again, my iPad is frozen. Okay, it should work. Okay, let me give it some time with my iPad to get unfrozen. So I'm asking is that as epsilon goes down to 0, is there an absolutely continuous curve such that this curve with jumps will converge to this absolutely continuous curve as epsilon goes down to 0? Okay, so that's what I'm asking here. Okay, why? Such that rho t epsilon converges to rho t, let's say locally uniformly. Now, if there is such absolutely continuous curve rho t, I can write it down in terms of continuity equation. But more importantly, what I want to know is that can this curve rho t be interpreted as a gradient flow? Well, if it's a gradient flow to what? I know that it converges to e to the power minus f. So can it be interpreted as a gradient flow of something which is minimized at e to the power minus f? Is this limit a gradient flow? Do you see what I'm saying? Why would I try to do this? Well, one reason that you want to try to do this is that you want to get some uniform estimate of convergence over epsilon. If this curve converges to a limiting curve rho t, which is a gradient flow, let's say of Kullback-Leibler, which is the actual thing, in that case, one can understand at what rate does this gradient flow converge as epsilon equals to 0. Because if that converges exponentially fast, and you have some control over the convergence as epsilon goes down to 0, then you can say that for all small enough epsilon, this is converging exponentially fast. So that should be one way of doing this. The other reason that you might want to see is that, okay, what is the underlying geometry that is determining the convergence rate of this of the synchronous algorithm? Because if there is a gradient flow, if there's a geometry underneath, I can essentially try to understand when this geometry will say that, okay, this is faster, this is slower, what is actually happening. Make sense? Do you guys understand the question that I'm posing here? So what am I doing here? I'm thinking of the iterations number of synchronous algorithm as time. But time with steps epsilon, where epsilon is my regularization parameter. And then I'm placing it in continuous time, and I'm keeping intermediates as just constant. And so I get this curve. And now as epsilon goes down to 0, I'm asking if this becomes a continuous curve, an absolutely continuous curve. And even more, does this absolutely continuous curve, is this a gradient flow of Kullback-Leibler? But then the question is, what is the underlying geometry? Any questions? All right, okay.
I'm just reminding myself,
Sorry, go ahead.
like, about
Mhm.
this locally uniformity and trying to think how that's important.
Forget about local uniformity. Just ask the question that for every fixed t, does rho t infinity converge to rho t in the Wasserstein space?
Mm-hmm.
So forget about local uniformity. Even that's something. Any other questions? And so the answer in our paper, as we discover, is the answer is yes, that this is actually a gradient flow. And this is a gradient flow of Kullback-Leibler. The answer, and this is in our paper, that the answer is yes, yes, there exists a limiting rho t, this curve. This curve is the gradient flow of the KL with respect to this e to the power minus f. So I'm converging to e to the power minus f as t goes to infinity. It's a gradient flow. But this is not the auto gradient flow. This is a gradient flow which is a generalization of auto given by this mirror geometry. The geometry is a mirror geometry. So let me explain what do I mean by this. Let me explain what do I mean by this. So what did I do here so far? Is this answer clear? There is a limiting curve. That curve is a gradient flow of Kullback-Leibler with respect to e to the power minus f. This is the marginal, the one marginal of syncon that I'm converging to. But the underlying geometry is not the mirror geometry. It's not the regular Euclidean geometry. In that case, I know this would be given by the Fokker-Planck equation. It is not the Fokker-Planck equation. It's something entirely different. And the geometry is a mirror geometry. So let me go back to what the mirror geometry was. Let me recap this thing here. So what did we do for the mirror geometry? We did the following. That I took some strictly convex function u. For every probability measure rho in P2 of Rd, I changed my metric tensor by, instead of taking my L2 geometry, I looked into V transpose Hessian of uv rho x dx. So some kind of geometry given by this Hessian. And now that distorts the geometry of the Wasserstein space. And now I can ask about what is the gradient flow of Kullback-Leibler with respect to mu. Now the geometry that appears in the syncon limit is slightly more complicated, where I'm going to pick my function u depending on this choice of rho. So let me explain. So what you do is that, remember, there is e to the power minus f is my x marginal. My e to the power minus v is my y marginal. And my syncon is trying to converge to these two marginals, e to the power minus f and e to the power minus g. Now take any rho in P2 of Rd. By Brunner's theorem, there exists some u rho Rd to R, some convex function, such that the gradient of u of rho will take my rho to e to the power minus v. Right? That will exist due to Brunner's theorem. Now at rho, I'm going to define my metric tensor by the Hessian of this u of rho. So v is in my tangent space of rho. You have to define the tangent space suitably, where I'm going to define the norm square of v to be gradient of v transpose of x, Hessian of u rho of x, then gradient of, so not gradient of v, just v itself, and then v of x rho x dx. Okay, so what have I done here? I'm doing something very similar to the mirror geometry, except I choose my mirror depending on my position. At every point rho, I'm choosing a mirror, which is my Brownian map mapping my rho to e to the power minus v. And that defines my tangent space at that point rho. And that gives me my some norm on the tangent space. That gives me some distance by some generalized Benami Brownian, by which I'm trying to minimize this distance. Whatever it is, it gives me some formal Riemannian structure on the Wasserstein space. And with this Riemannian structure, you should be very careful that this is a very singular kind of geometry, because this Hessian, it's not always defined. It's defined almost surely. There are lots of issues that things can go wrong. But assuming everything is nice, this can be defined. And so the answer is that this limiting rho t is the gradient flow of Kullback-Leibler of KL with respect to e to the power minus f in this new geometry. Okay. Do you understand at least some idea of what this statement is saying? So I have my syncon iteration, I have my syncon algorithm. Syncon algorithm is iteratively fitting my two marginals, e to the power minus f and e to the power minus g. I'm looking into the sequence of x marginals, which are not e to the power minus f, but they're converging to e to the power minus f. And as epsilon goes down to 0, at every single iterate, I'm not moving much. And so it makes sense to have time in steps of epsilon, and now let epsilon go down to 0 and get some continuum flow of measures. And ask, is this continuum flow of measures a gradient flow? The answer is yes, it's a gradient flow of Kullback-Leibler. This is with respect to e to the power minus f. But it's a gradient flow not in the Euclidean sense, not in the regular mirror sense, which I just described, but in the sense where I'm picking my mirror depending on where I am right now, my rho. So at every point rho, look into my Brownian map that is mapping to e to the power minus v, look at the Hessian, and I distort my tangent, this metric tensor there by that Hessian. And then on that geometry, the gradient flow of Kullback-Leibler is given by the limiting flow of syncon. How do you feel about this?
I'm trying to think how this might be used. Like, would we try to find such a U, if we start out with some problem and we have these fixed marginals and we want to know how Synchron's going to work?
Correct. So that was essentially our
Mm-hmm.
motivation. So our motivation was to basically think about, when can I say, as I said, that syncon always has that exponential rate of convergence as epsilon, uniformly as epsilon goes to 0. And this would happen if along the gradient flow, the Hessian of the Brownian map always remains bounded below. It means uniformly convex. But this is not always true. But there are conditions on the marginals under which you can guarantee that this is true. Okay. What this is saying, again, going back to this idea, what this is saying is that why do we see that syncon is sometimes fast, syncon is sometimes slow? The way we see this is because it's determined by this Hessian. So remember I asked this question that in the Euclidean case, when can you say that your mirror gradient flow is going to converge faster than Euclidean? And the answer was, at the minimizer of the function, I should have the Hessian of the mirror map to be very small. And so what you should expect here is near, the minimizer is at e to the power minus f. So near a neighborhood of e to the power minus f, if you have this Hessian of the Brownian map function to be very small, then you'll have very fast convergence. Otherwise, you wouldn't expect very fast convergence. So it brings this, it kind of lifts the Euclidean geometric intuition to when you should expect syncon to converge fast and when you don't expect converge fast.
So where's the master table that has all the things that do and don't converge exponentially?
We don't have that yet. Sorry, this paper is still in press. It should appear in Annals of Probability sometime soon. This is very fresh, so we don't know that.
Yeah. Yeah.
We have some strong sufficient conditions under which we know this is exponential convergence, but it's a great question. Where is the master table which will tell me when this is fast, when this is slow?
Yes, and I can just use things in that family and use Sinkhorn and go.
Correct.
Go
We don't know that yet.
Yeah.
Okay.
Do you think that this will guide choices of epsilon? This doesn't seem to
this
guide
is
choice of epsilon.
This is exactly several of us are basically thinking, well, it's not even clear that there is because from our experience, we know that there are marginals, e to the power minus f and e to the power minus b, where syncon is painfully slow. So one way to go would be to say that, okay, come up with sufficient conditions on e to the power minus f and e to the power minus v, so as a syncon is exponential convergence. And I think we are all the research is kind of converging that if they're sufficiently log concave, this is true. The other thing would be to come up with examples of e to the power minus f and e to the power minus v, for which this is not true. This is actually, this Hessian over here actually blows up and you don't actually get fast convergence. That would be very interesting too, because that will say there is certain regime where you should not expect syncon to converge fast as epsilon goes to 0. Good. Yeah, so, but this is all very fresh. These are all research questions. All right. Okay. There's another rather interesting connection to this. So this is one description of this limiting rho t. So this is description 1. And in our paper, we actually give 3 equivalent descriptions. So there are 3 equivalent descriptions of this process. So this one is 1, which is that this is a geometric description. There's a gradient flow of Kullback-Leibler in this new geometry. There's a description 2, which is this following, that if you look into this rho t, and this rho t is mapped by this function ut, or gradient of ut, to e to the power minus v. Okay, so ut is what I was calling, ut is my u of rho t. So this is my Brenier map. You can ask the question, what is u dot t? And that would give you some other PD. What is this PD? So what am I saying? I'm saying that instead of looking into what is the PD that is satisfied by rho t, which is this probability measures or densities, you can ask what is the corresponding equation that is satisfied by the Brenier potentials themselves. And the answer is that this is given by ut of x is fx minus v of gradient of ut of x plus a log determinant of the Hessian of ut of x. And this beautiful equation is what is called the parabolic Monge-Ampère, which again existed classically. It's not something we came up with. I'll explain what this means and what this has to do with the Monge-Ampère equation. So if you recall from Young's lecture, what does the Monge-Ampère equation do? So the Monge-Ampère equation tries to solve, so let's go back to Monge-Ampère equation. I know my e to the power minus f when I do a push forward by my Brenier map, which is, let's say, gradient of u. I get that this is e to the power minus v. This leads to the following Jacobian equation. This is the Jacobian equation when you do a change of measure. So if you do this Jacobian equation correctly, you would get that f of x minus v of gradient of u of x plus the log of the determinant of the Hessian of u of x is equal to 0. That's my Monge-Ampère equation. Okay, perhaps you remember it, perhaps you don't, but it's not very hard to derive this, that if you have a function u which push forwards e to the power minus f to e to the power minus v, if we write down the Jacobian change of measure equation, you will get exactly this, that this must be satisfied. This is equal to 0. Now look at what this parabolic Monge-Ampère is doing. It's just putting a ut dot to the left-hand side of the same right-hand side, which should be equal to 0. So you should think in terms of heat equation. This is a generalization of that same idea. So when you have, with the heat equation is ut dot is Laplacian of u. Now its solution in stationarity, when ut dot is 0, is a Poisson equation. That's where it's converging to. And so when you take ut dot is Laplacian of u, your solution ut is just converging to the stationary solution where the Laplacian is equal to 0, the Poisson equation. The same thing you should expect here. My Monge-Ampère is some kind of stationary solution. This is what I want to solve. But I would treat a dynamics where no matter where I start from, I would converge to the solution of the Monge-Ampère equation. What is a natural dynamic? You create a parabolic dynamic where on the left-hand side, you take time derivative of u, and on the right-hand side, you want the quantity that becomes 0 in the end. So as t goes to infinity, you expect that this should converge, and therefore ut dot would be 0. And then the right-hand side is equal to 0, and that would give me a Monge-Ampère equation. So it's a very natural way to create a dynamic out of something that you want to solve. Make sense? Something very natural. What we show in the paper is that this dynamics and this description 1 and description 2 are equivalent. So in the sense that if you solve your gradient flow of Kullback-Leibler in this new geometry, and then you define ut to be the Brownian map that sends rho t to e to the power minus v, then that solves the parabolic Monge-Ampère. Conversely, if you take the solution of the parabolic Monge-Ampère, and then you push forward e to the power minus v by gradient of ut star, the convex conjugate, then the resulting rho t is this gradient flow of Kullback-Leibler. How are you feeling about this? So I'm giving two equivalent descriptions of the same limit of syncon. One is by describing how the marginal flow is converging by some geometric description. And the second one is saying, okay, let's always fix the y marginal and track how my Brownian map is converging, evolving. And that's a parabolic Monge-Ampère. Good.
I have a quick question.
Yes, go ahead.
So here, after we get this iteration given by synchrony, then we use a piecewise constant interpolation to get a curve of measure, right? So
that's right.
If we use another type of interpolation method, do we still have the convergence?
You should expect, because we show convergence locally uniformly. So if instead of having, let's say, piecewise constant, you join them by interpolating lines, you should expect the same limit.
Okay.
Yeah, that's not a problem.
Okay, thank you.
Any other questions? Okay, and now I'll give a third description in terms of a stochastic process. So I know that for my Langevin diffusion, which are my gradient flow of Kullback-Leibler, so the marginal densities of Langevin diffusion gives me gradient flow of Kullback-Leibler. I just also talked about the mirror Langevin diffusion. This is my mirror Langevin diffusion, and the gradient and the marginal distribution of the mirror Langevin diffusion gives me the gradient flow of Kullback-Leibler in the mirror geometry. There's also a same thing here, the same diffusion that I would get here. And the only change from the mirror Langevin diffusion is that this u will now depend on the law of xt. That's all. Okay, this u is not the same u over time. It will depend on the law of xt. But otherwise, it is exactly the same mirror Langevin diffusion. It's a non-stationary version of the mirror Langevin equation. So that's a third equivalent description of the process. So description 3, So rho t is a marginal flow of the solution of the following SD, which is dxt is equal to minus gradient of v, gradient of ut of xt dt, plus square root of 2 Hessian of ut of xt inverse dbt. Okay. So this is some, now you should remember, so what is ut? So ut, when I take rho t, I push forward rho t by gradient of ut, I guess e to the power minus v, and where rho t is the law of xt. So this is an example of what is called a McKean-Vlasov equation. If you have heard, this is a very, very popular class of diffusions. If you have heard of it, you know what I'm talking about. If you have not heard of it, it's a class of diffusion whose behavior depends on its current distribution, current law. So look at this, its drift and its diffusion. If you want to calculate the drift and the diffusion, you need to know what is the law of the current value of the current coordinate. But then the dependence comes through this Brunier map, transporting the current law to the e to the minus v. So as you can clearly see, this is the same as a mirror-Langevin diffusion, except that you also evolve your convex function. So in terms of the mirror geometry, what I'm doing is that at every row, I'm using a different mirror geometry, a different Hessian geometry, where the Hessian space is given by the Brunier map, transporting rho to e to the power minus v. Okay, so these three are equivalent descriptions of the same limit, and that's where the synchron iterates are converging to. And so if you can show that things are converging fast or slow in either of these three descriptions, that will automatically imply that synchron is either fast or slow for small temperatures for those two marginals, e to the power minus f and e to the power minus v. Okay. Anything else? So as I said, so this is, this is all very fresh. The paper is still not out. It's still being, it will come out in the Annals of Probability sometime soon. A lot of current work is going on in this direction. It's a very, very exciting area to understand the details of this synchron or such algorithm. It's not just synchron algorithm. People have also figured out similar structures appear in other kinds of algorithm, like Gibbs sampling. So you want to understand the limits of these algorithms in a geometric way by distorting the autogeometry. It's a very active field, lots of interesting problems. If you have any questions, I'll be happy to answer. Right, okay. So if not, we'll end here. So next week, I think Monday, Youngman is teaching. Rest of the week is Thanksgiving in the US. So happy Thanksgiving, you all. Okay. If there are no other questions, goodbye.